Hello, we continue to explore basic properties of the Riemannian manifolds. Today I will mention about the parallel transport. Parallel transport. This topic is a little bit theoretical topic, but it's very important, so we need to mention about this. So first let me give one lemma. Let M be a Riemannian manifold. Riemannian manifold and alpha, which is defined in this way, a curve. So suppose if x belongs to this tangent space, here t sub 0 belongs to I, then there is a unique vector field, actually parallel vector field, parallel vector field along alpha. So it means we have this one. Such that x t sub 0 will be x. Actually, this implies the existence of the geodesics on Riemannian manifold. So let me show this one. Now suppose this x1 to xn is a frame field of M. So it means at some certain point it will be the basis of the tangent space. So we denote this one d dt x as xi as j goes 1 to n aij xj. So aij differentiable functions. Okay. Also, if you have vector field, let's say this one, then you can write x I goes from I to n hi xi. So this is a vector field on the manifold. Now let me write this one. So you can write there is x here. Hi xi. So now apply the rule of the linear connections. Then we have, let's say here, thi dt xi plus hi ddt xi. Now if you use the above representation, then you have this one. Hi. So here you can write j goes from 1 to n aij xj. Now here these I and j indices are on the same set, so you can write this one, J DH J dt plus I goes from A1 to N, so A J HI. So then you can write this one, xj. Now, so it means nabla d dt x equals 0 if and only if you have this one. So let me remove this part. So, but if you look at this one, this is the ordinary differential equations. So, for initial conditions, let's say H1, Hn, we have unique this system, let's say this one, let's say I has unique solution. So it means if you have this one for x t sub 0 x, then it will have unique solution. This proves our assertion. Okay. Okay. Now we can define the parallel transport. Sometimes they call this one parallel translation. So again, if you have Riemannian manifold, and alpha a curve such that so for t sub 0, let's say t1, yeah, t1, t2, t1 and t2 belongs to I, alpha t1 p, alpha of t2 q. Then for parallel vector field x such that x t1 tpn, then this map p t1 t2 alpha goes from tpn to tqm. So it takes x here, so goes to this one, x. So this one is, let's say z as a vector, so xt2. This map is called parallel transport. So it takes this vector to the another vector along the curve, of course. So first I will draw this map p t1 t2 alpha is a linear isometry. So this parallel transport is a linear isometry. So first let me remind this one. If x and y are parallel vector fields, then x plus y is also parallel. So if you say xt1 x, yt1 y, then x plus y t1 will be x plus y. Okay, first I will show this map is linear. So to show this one, pt1 t2 alpha x plus y. So then this one is, it will be like z, but this one is x plus y t2, right? So you can write this one x t2 plus y t2, and this one is actually p t1 t2 alpha x, the other one p t1 t2 alpha y. Okay, so this is the first part. Also, if you choose this c, then p t1 t2 alpha c times x will be c times p t1 t2 alpha x. So it's linear. Okay. Now we will show that this is a linear isomorphism. So to show that, we need to show it is a one-to-one and onto. The first, if p t1 t2 alpha x is 0, then previous lemma shows that, because it is unique, then this x t1 0, so it means x 0. So this p t1 t2 alpha is 1-to-1. Okay. The onto case is clear because if you look at the dimension of TPM and dimension of the TQM, so that's why alpha is onto. So these all shows that this P T1 T2 alpha is a linear isomorphism. Okay, now we need to show that this map preserves the metric. So it means we need to use this one. We need to show that this one, let's say G is a Riemannian metric, P T1 T2 alpha x y, P T1 T2 alpha y is equal to xy. We need to show this one. But first, because G is a Riemannian metric and nabla is a Riemannian connection, it means you have this one. Or we can write this one, right? T2 gxy. So g nabla x y plus gx nabla d dt y. So this is 0. Why? Because it's parallel and this one is parallel. This one is parallel. So this shows that gxy is constant. So because it's constant, it means it will take the same value for every input. So I can write this one. So alpha now x p t1 t2 alpha y. So by the definition of the parallel transport, you have this one x t2 y t2. But because we know that this constant, I can write this one also. But this one is gxy. So conclude that p t1 t2 alpha is a linear isometry. Because it also preserves this metric. So the length of these vectors will be same under this map. Okay, so far so good, because we showed that algebraically this map is a linear isometry. So this is very useful for us when you do calculations or when you define something on the Riemannian manifold. But what is the meaning of this map? Let me mention about this one. When you consider the plane or the Euclidean space, then if you have a vector here, let's say it is P, and when you move this one, let's say here, it will be same, right? Same way. So this Q, V, P. But if you consider, okay, let me. Okay, if you consider another curve, let's say this is our sphere. Okay, so let me consider these. Okay, let me consider these. So this sphere, this is this is the center. So I consider this curve. Okay, so this is geodesic. We know that for the sphere. So consider a line here. If you look at this line is, so let's say this P and this VP. So here, this is tangent to this curve, right? This curve. Okay, this one is tangent. But when you move to this one on this curve, let's say you come to this point. So this is your VP. And this point is now, let's say, Q. If you compare these two vectors, here this vector is tangent to this curve, but here is not. So here the parallel transport takes its action. So then you apply this. Okay, this one. So this now is tangent. So we say this one VQ, and VQ obtained by T1, T2 alpha, VP as VQ. Of course, if you look at here, our parallel transport is a rotation, but in some other manifold or some other situations, it can be some other map. But here it's a rotation. So you see behavior of this map, this vector field will be same here at this point by using this parallel transport.